Hey everyone, I'm Angie, and today I'd like to show you how to become a master of circuit design using Kirchoff's current and voltage laws. Here's a simple circuit with an LED, a resistor, and a button. When I push the button, I allow current to flow, enabling the LED to light up. As a designer, I want to know how to control how bright the light is. I need to know how much current will flow and why, and what I can change about the circuit to have control over it. So let's figure out how this circuit works. When I press this button, I'm actually creating a node because I'm creating a connection between the resistor and ground. There's also a node at 5 volts and another node between the LED and the resistor. Why do I care about nodes so much? Well, there are two circuit laws that I can use in order to calculate the voltage and the current running through my circuit. And knowing these will tell me how the circuit works, and that enables me to be a good designer. These laws were first described by a physicist in the 1800s. And his name was... Okay, there's a lot of debate on how to say this guy's name. Kirchoff? Kirchoff? When I was an undergrad, I just said the first thing that came to my mind when I saw the word, which was Kirchoff. I've heard people say Kirchoff, which rhymes with beer cough. You know, beer cough. Beer cough. I went on Reddit and saw a post where someone said that the actual German pronunciation of the word is Kier, cat hissing noise, off. So, Kier, off. How'd I do? Well, it's supposed to be during like Kirchoff, Kirchoff. I'm just going to say Kirchoff because that's what I'm used to, or I might say something else because I just confused myself by saying it a bunch of different ways. If I'm saying it wrong, just let me know in the comments, and I'll fight you. The two rules for nodes are called Kirchoff's current law and Kirchoff's voltage law, or KCL and KVL for short. KCL describes what happens to the current flowing through a node. Whatever comes into a node must go out. Current cannot accumulate. It can't just disappear and reappear out of nowhere. So in this circuit, there is current through the LED and current through the resistor. The current from the LED comes into the node and it leaves through the resistor. So the LED current and the resistor current are the same. KVL describes the voltage at a node. Note that I didn't draw a node here because the button is not pressed in this diagram. But when I do press it, it becomes a wire and a node appears. What this means is that if I take the voltage across here, so from this node to this node, and add it to the voltage here, from this node to this node, I would get the voltage from this node all the way up to this node. If that didn't make sense to you, check out my previous video. I eat exactly 2/5 of a pie to make a point. Definitely check it out. Here's another analogy looking at this from the ground up. You know how in a video game, how you fight a boss at the end of each level, and then you get to the final level, and the boss is super hard because he's basically the sum of all the bosses that came before him? Same basic principle. In this circuit, the voltage across this resistor is the voltage from this node to ground. We'll call this VR. The voltage across the LED is the voltage from 5 volts to this node. We'll call that VLED. So the voltage across the LED plus the voltage across the resistor must equal 5 volts. I can also use Ohm's law here. For resistors, the voltage across the resistor is the current through the resistor times the resistance, or V equals IR. Now, Ohm's law can only be applied to resistors, so I can't use Ohm's law on the LED. But I know from experience that LEDs need about 2 volts in order to work. So VLED equals 2 volts. So that tells me that the voltage across the resistor is 3 volts, according to Kirchoff's voltage law. Now I can use Ohm's law to find the current through the resistor. IR equals 3 volts divided by 1K ohm, which equals 3 milliamps. And that must be how much current goes through the LED because ILED equals IR. According to Kirchoff's current law, if the LED is too dim, you can increase the current by decreasing R. If the LED is too bright, then make R bigger. Let's make the circuit a little more interesting. So here's my original circuit diagram. And now I'm going to do something crazy that I haven't done yet. I'm going to split the circuit at this node and draw the mirror of the circuit over here. I have another resistor with the same amount of ohms and another push button here, and they both end at the ground node. Ooh, what's this going to look like when we build it? So here you can see I've created a mega node with this blue wire. So this node on the circuit diagram is this blue wire. Once you've built this, experiment with the circuit and see what happens. Go ahead, I'll wait. Actually, no, just pause the video or build or just keep watching. I'm easy. So we see that if no button is pressed, the LED is off. Pushing one button or the other completes the circuit and the LED will turn on. The LED, as you can see, has the same brightness when either button is pressed because these resistors are equal. Remember that when a button isn't pressed, it's like that branch of the circuit doesn't even exist. It's not connected, which means that if we press this button, then the circuit starts here, goes this way, and ends here. But if we don't press this button and press this button instead, then it goes this way. What if I press both buttons at the same time? Do I dare? Just kidding. But what will happen is that the light will get brighter when both buttons are pressed. See, this is me pressing both buttons, and if I let go of one of them, you'll see the brightness goes down. To see why, use KCL and KVL to evaluate your circuit. KVL will help you find the voltage across the resistors. Ohm's law will turn the voltage into a current, and KCL will tell you where the current goes. So we're using KVL to find the voltage across these resistors. The voltage across the left resistor plus the voltage across the LED equals 5 volts when the button is pressed. When this button is pressed, the voltage across this resistor plus the voltage across the LED also equals 5 volts. And keep in mind, the voltage is 3 volts in all three situations here. So the voltage is 3 volts when the button is pressed on this side, the voltage is 3 volts when this button is pressed, and the voltage is still 3 volts at this node when both buttons are pressed. So the current through the left resistor, I'll call that RL, equals 3 volts divided by 1K, which equals 3 milliamps. And the current through the right resistor is also 3 milliamps. Now use KCL to find the current through the LED. So I'm going to call this current I LED. That comes into the node, and then IRR and IRL come out of the node. So I LED equals IRL plus IRR. So the current through the LED when both buttons are pressed is 3 milliamps plus 3 milliamps, which equals 6 milliamps. So that totally explains everything. When I press one button, the current through the LED is just 3 milliamps. But when I press both buttons, it adds up to 6 milliamps. And that's why the LED is brighter when I press both buttons. So as you can see, KCL and KVL help me pick apart my circuit. I can find the current and the voltage at every node, which allows me to design a circuit that works exactly the way I want it to. Until next time, I'm Angie. Thanks for watching.